All right, so I'll start doing that today. So this particular recording will be, I believe, I hope I did it right. Will be on the under this week's module. All right. So this let's go over the test. It's going to be on the test for the next half hour or so, and it does cover chapters 7 through 12. Multiple choice as before. So I'm going to go over chapter by chapter, and then if there is a particular topic that I need to go over in more detail, I will. I just finished a session with some students on how to use Microsoft Excel, so I'm going to show you the use of that for answering certain types of questions on the test. All right. Now, chapter 7 has information about different types of summary statistics, such as the mean, the median, information about different types of plots, such as the histogram, and stem plot. Box plots are in here also. Standard deviation and variance, also mentioned in this chapter. So the question is, what can we find from this chapter? Well, there's quite a bit of information in here, so I would think I think you would think that the test would emphasize this chapter maybe a lot, and it does. The test does have a few questions from this chapter. So the types of questions I could ask could be based off of definitions, the mean, the median, that sort of thing, and how to calculate them, obviously. The other thing I could do is I could ask you to look at or describe certain types of graphs or distributions that are skewed versus bell-shaped. On page 147 of the textbook, it goes over what skewed left and skewed right means, right? Skewed left means that the data set is more spread out on the left and more clumped or packed in the right. Okay, so it sort of tails off to the left if you were going to draw a curve. Skewed to the right means that most of the data the higher values are more spread out and the lower values are clumped together, so it sort of tails off to the right. That's why it's called skewed right. Now, if the data set is skewed right, typically you may have some outliers or unusual values which are on the high side. And what happens is the mean or the average tends to get higher than the median. All right, so the mean ends up being higher than the median. Now, if it's skewed right, that means most of the data is to the left, and so your mode is low. So the mode is low, then the median is usually a little bit bigger than the mode, and then the mean is higher than both of them. So for skewed to the right, the mean is the largest number, typically. The median comes second, and then the mode comes third. If it's skewed to the left, which means the data is more spread out on the lower end, that means there's probably some unusually small outliers. The small outliers are making the mean smaller than the median. Right? So if it's skewed to the left, it's tailing off to the left, and most of the data is towards the higher values, right? So it's clumped to the right. So that means that the mode is the largest typically, then comes the median, and then comes the mean. All right? So let me repeat that again. Skewed to the right means what? It means the mean is bigger than the median, is bigger than the mode. Skewed to the left means the mode is bigger than the median, which is bigger than the mean. All right. Now, if it's symmetric, then the mean, median, and the mode are all approximately equal to each other. Okay, so that's the type of question I could ask on, or questions I could ask on your test, is I can give you information about the skewness and then ask you something about the mean or median. That certainly could be a question I ask. That's also asked typically on the final exam too, so that's why I considered it an important exam question. Any questions about that? Again, it's explained pretty clearly in this chapter 7. So definitely review the video again of chapter 7 if you're not clear about these things that I've talked about. Now, outliers. Again, outliers are unusually large or unusually small values compared to all the other values in the data set. Now, how do you identify an outlier? They do explain it, I believe, in this chapter. So let me see if I can find it for you. Yeah. Outliers tend to show up on what's called a box plot. Remember what a box plot is? Box plot breaks up your data set into 4 quartiles, or equal quarterly pieces, 4 equal pieces. And that information starts on page 149 and goes for the page before that, on page 148, it talks about what's called the 5-number summary. It's a box where they have 5 numbers inside the box, which are the median, the lower quartile, the upper quartile, and the smallest number and the largest number in your data set. Okay, so it shows you how it's represented in this textbook with this rectangle and inside those 5 numbers. So if you see one of those rectangles, you should be able to identify, and remember you have your book available, right? You should be able to identify which number is which. Now the box plot is a visual aid in describing these 5 numbers, right? Because that's the box plot is created from these 5 numbers. Now, in addition to a box, which is in the middle, and these whiskers, sort of these horizontal or vertical lines that come out of the box, there's typically the asterisk, which represents an outlier that's also drawn on a box plot. So whenever you see an asterisk, that means it's an outlier. On page 150, it describes how to calculate an outlier. So you need to know this. So that's why you need, your calculator by your side if you need to calculate what an outlier is. The first thing you need to do is calculate what's called the interquartile range, which is the difference between the upper quartile and the lower quartile. You need to subtract those 2 numbers, and you get this thing called the interquartile range, which is really the distance across the box that you're looking at. It's the actual distance in units across that box of the box plot. It represents, by the way, the middle 50% of your data. Now, to calculate an outlier or figure out whether you have any outliers, you take that calculation of the interquartile range, or IQR as they call it, and you multiply it by 1.5. And once you've multiplied the IQR by 1.5, what you do is to see if there's any large outliers, you add that 1.5 times IQR, you add that to the upper quartile number. So you add those 2 numbers together, the upper quartile number and the 1.5 times IQR. And whatever number you get, if you have any numbers in your data set that are larger than that number, that is considered to be an outlier, a large outlier. Now, to find out if you have any small outliers, what you do is you take that 1.5 times the IQR and you subtract it from the lower quartile, and you get a number. Any numbers in your data set that are smaller than that number is considered to be a small outlier. All right. So if you see if you see a box plot, then they're represented by an asterisk, the outliers, either on the large side, the long side, or this on the short side. All explained on page 150 is an example there of how to do that. Okay. If I don't give you a box plot and I ask you something about whether a value is an outlier, that's what this procedure that you see on page 150 is what you have to refer to. So if I were you, I would tag that page, make sure it's you reviewed it obviously beforehand, but you tag it so you can get there pretty quickly when you see a problem that requires you. Determine if you need determine if a particular value in your data set is an outlier, and that way you can do your calculation and make your decision. Okay. So that's one possibility for your test. Another possibility is I will give you a histogram. What is a histogram? Histogram represents a quantitative or measurement variable, and it's just a bunch of rectangles, right, that are adjacent to each other. And the rectangles along the x-axis is the values of your quantitative variable, the numbers associated with that. And then along the y-axis could be one of two things. It could be your frequency or count, or it could be a percent. Okay. So it's either the frequency or a percent. What does percent mean? It means the percent of it would basically be for that particular rectangle the frequency, the count for that rectangle divided by the total frequency. That means the total count in your whole data set. How many values are in your data set? That's percent. I can give you the y-axis either as a frequency or percent, and then I can ask you questions about just very general questions. I can ask about that. I can ask you. I mean, even in the book they talk about the shape of the distribution, whether it's skewed left, right, or symmetric. That's certainly possible. I can ask you what percent of the data is above or below a certain value. I can ask you questions like that. That's it. I mean, I can't ask you too many more questions than that, because we didn't go into we didn't go into how to create one of these histograms, right? In a real statistics course, actual statistics course, you would probably learn how to create a histogram. And in this course, I'm going to give you a histogram. If I'm not going to ask you to create one, and then I just can ask questions like that. All right. Any questions about histograms? Again, they are described starting on page 144 through 147. They give a couple of examples of a histogram. Okay, so just go through the examples. It shouldn't be that difficult. The one I give you, if I give you one on the test, it's not a difficult one to evaluate. Pretty easy one, I think. All right. Then chapter 7. If I give you a data set, data set could have more than one variable, right? We could have an X and a Y. I could also ask you about the mean or average for the X or for the Y, and the standard deviation for the X or Y. Okay. Now I'm going to show you an example with Excel in a few minutes. Once we get towards, maybe in about half an hour or so. One of the last things I'll show you is using Excel to maybe answer some of these questions. All right, chapter 8. Deals with the bell-shaped curves. In this course, we're not going to go into great detail about using formulas for bell-shaped curves. So what I can do, however, is one thing that you should be able to do is, if you have a list of maybe scores on a test or something like that. And if you know the mean and you know the standard deviation of that test, you should be able to convert the raw scores, the original scores, into a standardized score or a z-score. And how do you do that? You take your original score, your raw score, you subtract the mean, and then whatever you get, you divide by the standard deviation. And that's called a standardized score or z-score. And that number tells you how far away from the mean your raw score is, how many standard deviations away from the mean. Now, if your standardized score is negative, it means that your score is less than the mean. And if it's positive, it means it's greater than the mean. If you have a standardized score that's 0, it means it's exactly equal to the mean. All right, so that's one thing you can do. I can ask you to do. Percentile, the definition of percentile, what does that mean? Percentile means the percentage of the population that scored less than you. Okay? Scored less than you. So that's something that you should know, what a percentile is. And it's explained on page 168, chapter 8. Now, when we were going over chapter 8 in class, there was a table in here that I said you could possibly use, but I really should not be encouraging you to use a table because this is more of a regular stat course type item. So what I'm going to ask you, I'm just giving you a heads up, is I'm going to ask you something about, or ask you to calculate something based on what's called the empirical rule. That's on page 173. The empirical rule says if you have one of these bell-shaped or normal curves, it says that if you know where your mean is, now the mean is it's symmetric, so the mean is right in the middle, and the mean is equal to the median. It says that approximately 68% of your data set should fall within plus or minus 1 standard deviation from the mean. Okay. So you take your mean and you add 1 standard deviation, take your mean and subtract 1 standard deviation, and those two numbers that you come up with, about 68% of your data set's in between those two numbers. If you add and subtract 2 standard deviations from the mean, that is, you multiply the standard deviation value by 2 and add and subtract it from the mean, 98.5% of your data set should fall between those two values. And then it says if you add and subtract 3 standard deviations from the mean, then you have almost the entire data set. 99.7% of the data set should be between those two numbers. Again, it shows you how to do it on page 173. And that's how you come up with your answer. So whatever I ask you to do on your test, I'm going to ask you to use the empirical rule. Now, what if I asked you something like the following with the empirical rule? What if I gave you somebody's raw score, and then I gave you somebody else's standardized score, and then I give you the mean and standard deviation for the test, and I ask you what percent of the population scored between those two scores. So what would you do? Well, the person who had the raw score, you should convert it to its standardized score by using that formula, the standardized score formula, by subtracting the mean and dividing by the standard deviation. So you should take that person's raw score and convert it into the standardized score. The other person we already have their standardized score. So what you're being asked is to find the percentage of people between those two standardized scores. So how would you do that? Well, if one person had, let's say, -1 as their standardized score, and the other person had +1 as their standardized score, well, between -1 and +1 is 68% of the score should be in between those two, because the -1 represents 1 standard deviation below the mean, and the +1 represents 1 standard deviation above the mean. So between -1 and 1 should be 68%. If it's between -2 and 2, 95%. But what if after you've converted to the standard score, you find that one of the scores is, let's say, -2, and the other one is +1? How would you figure out the percentage between those two? Well, you would use the symmetry, the idea of symmetry of one of these normal curves. If you're on page 173, you notice that 95% of the curve is in between -2 and +2. I guess you don't see it on this curve itself, but just know between -2 and +2 is 95%. So what's left? 5%, right? 100% minus 95% is 5%. And half of that 5% will be found on the left side, the remaining area on the left side, and the remaining area on the right side will be half of 5%, which is 2.5%. So how would you find the area in between -2, standardized score, and 1? Well, the area to the left of -2 is going to be 2.5%. Now, the area, now you go on the other side of the curve, the right side, and you're going to you want to know what's the area to the right of +1. Well, if 68% is between -1 and +1, standardized score, that means 32% is left. 16% on the left, 16% on the right, half on the left, half on the right. So the area to the right of +1 is 16%. All right, so we're almost there. The area to the left of -2 is 2.5%. The area to the right of +1 is 16%. Add those two areas together, you get 18.5%. All right, so what's the area in between -2 and 1? It's 100% minus the 18.5%, which comes out to 81.5%. So hopefully through words that wasn't too confusing, but that's how you would do a problem like that. And that's about all I can ask you using the empirical rule, is asking you area in between two standardized scores. So don't worry about the chart that's on page 175. You don't need to use it. If you want to use it, you can, but not unnecessary. Okay. Any questions about chapter 8? Again, just make sure that you understand that empirical rule. And I guess that's it. Now, and also, of course, how to calculate the standardized score. Obviously, you need to know that too. Now, chapter 9. Chapter 9 has some other graphs in here. Pie charts, bar charts. Some of these graphs are for categorical data, right? Which are they used for categorical data? What type of data is that? That's the data that can be described in words. Those are labels. All right. So the pie charts, the bar graphs, pictograms, those are all used for categorical data. Pages 182 to 184 shows you those types of graphs. After that, there are other types of graphs which are for measurement or quantitative data, such as the line graph, the time series plot. Okay. And the only thing I can ask you here is just some information about maybe a couple of these plots, like the time series plot, for example. Running along the x-axis would be time, some measurement of time, like months or years. And then along the y-axis could be some sort of quantitative variable, whatever it might be. In the book here, it explains what would be an improper presentation of a time plot, but just know also the components of a time series plot. There's a trend, or long-term trend. There are seasonal components which occur periodically, depending on the time of year. And then you have these other things called the irregular cycles, which don't happen once in a while, but not on a regular basis. And then random fluctuations, which nobody can explain. Okay, so just be familiar with that page. Talks about a time series plot, just know components of it. And not much else in this chapter. There's not a whole lot going on in chapter 9. Chapter 10 is an important chapter, all right, because it does deal with the linear relationship between two variables, right? And it talks about correlation. So you obviously need to know the definition and also how to calculate correlation. And I will show you an example using Excel, how to calculate correlation. Just know what correlation is, and it represents a measurement of the linear degree of connection or relationship between two quantitative variables in terms of a linear measurement. All right. So, so a correlation does not measure a nonlinear relationship like a curve. And the closer the points are to a line, the larger the correlation is in terms of an absolute value. The correlation runs from -1 to +1. -1 meaning what? Perfect negative correlation. That means all of the that means this line, as you go, if you graph the points, the line goes down from left to right. It goes the slope down, and all the points are exactly on that line. That's perfect negative correlation, -1. Most data is not perfect, so if the points are around the line, then the more scattered they are, the smaller the number is, or closer to 0 that number is. So a strong linear relationship means that points are close to the line. A weaker linear relationship means that they're more scattered further away from the line. But the correlation would be negative if it's sloped downward. If you picture a line going through those points, it would be sloped downward, and it would be sloped up. It would be positive if it's sloped upward. Okay. Correlation does not imply causation. This is very important. Correlation does not imply causation, which means if you see a strong correlation between two variables, it does not mean that the two variables, that one variable causes the other. It could be that it could be a cause and effect relationship, but it doesn't mean it's 100% sure. There could be some other variable that's causing that situation, or other variables that could be causing the situation. It could be coincidental too. It's possible it's a coincidence. So there's a whole bunch of reasons why you could have a strong correlation. They give examples in here about correlation, and they're all good. So you should look through all the examples. But know that the calculation of the correlation can be done in Excel. Probably the easiest way of doing it. Now, I did in my little meeting before this class, there was somebody on Google Sheets. So if you're going to use Google Sheets, you're able to use the same function for correlation as you do in Excel. And you can also find the slope, the y-intercept of the regression line. That's the best fitting line that goes through those points. I mentioned before that you didn't need to calculate it, but in Excel, it's so easy that I decided that if you're going to calculate correlation, you might as well calculate slope and the y-intercept too. And I'll show you how to do it. It's very easy. It's just as easy as correlation. Now, on page, starting on page 10, is a definition of what regression is. Regression basically is an attempt to draw a best fitting line through a scatter plot of these points that have a relationship between two quantitative variables. This regression line is a straight line that has a slope and y-intercept, just like any other straight line. Another name for the regression line is the least squares line. Okay, least squares line is another name for it, because that's the mathematical principle behind it, which you don't need to be familiar with. Just know that the closer the points are to the line, the bigger the absolute value is of the correlation. Closer the correlation is to either -1 or 1. The more scattered the points are, the closer it will be to 0, which 0, by the way, correlation means there's no relationship at all. All right. And it does describe how to find the correlation in the book using CORREL, I believe, but I'll do it in our example in a minute. And then on page 213, it shows you the Excel function of slope, which will find the slope of the regression line, and also intercept. This is the other function in Excel, which gives you the y-intercept. All right. So I'll show you that example as the last thing we'll do. Then on chapter 11 doesn't have much in it, but it does have information about what is considered to be a legitimate correlation as opposed to illegitimate. You may want to read through that. It mentions on page 233 that legitimate correlation does not imply causation. I would read through chapter 11 for sure. It may help you answer a question or two on the test. You definitely need to read through it. Now, if the correlation is very low, close to 0, and you have a regression line, that regression line is pretty much useless, all right, in terms of predicting y from x. It's not very good at predicting. So if the correlation is close to 0, then the regression line is not really, it's not a good predictor. So just remember that. On page 235, it says some reasons for relationships between, to have relationships between variables. That means to have correlations between variables. You may want to read through that list. There's a list of 7 reasons why you could have correlations, but not necessarily have causation, although causation is one of the reasons here. And then on page, let's see, find the page here, page 240, I would also look at that page also, because it says possible reasons why you may think there is a cause and effect relationship, even if you're looking at an observation. Gives you 4 reasons. So make sure you pay attention to that page, page 240. And then chapter 12. This is the one that probably the most difficult of the chapters. And this here, I'm going to show you an example of, I think I went over it last time, but I'll show it to you again, of how to calculate from a table. Now, this table here is a table between 2 categorical variables, right? These aren't quantitative variables. And so the best thing to do is look at an example of this. So let me, give me a second here. Let me, oops. Let me open up. Hold on a minute. I gotta get through this way. Give me a second. I have to get the PDF that I was using the other day. And then I want to show you the Excel spreadsheet too. Let's see. Yeah, this is it. All right. So I think I can find it now. All right. I don't know what's going on here with my computer. Oh, here we go. All right. So this is a chapter 12 type question. Here's a contingency table. Ethnic group. Now, typically, if you think there's a cause and effect relationship, the explanatory variable, or the X variable, you could say the X variable, is running along the rows. So in this case, it's the ethnic group, African American and white is the ethnic groups. And then along the y-axis, along the columns here, is the response variable, which is the Y. And it's basically asking the question whether you were laid off, yes or no. And inside each of these cells here are the counts, okay? And the grand total is this number towards the right, the lower right. That's your grand total, number of people in the survey. And you can ask questions like, what's the percentage of African Americans who were laid off? That would be 130 divided by 1512. There's 1,512 African Americans. 130 were laid off. You can also ask how many were not laid off. That would be 1382 divided by 1512. I hope you all know how to convert a decimal into a percentage. You multiply by 100. You can also express your answer as a rate. All right, so percentage, it says 8.6%. If you want a rate per 1,000, just multiply that by 10. Okay, so you can ask questions like that. You could also now these answers here that you got here are also can be considered to be the risk of being laid off. The same number, 130 divided by 1512. You could also say it's the probability of being laid off. Okay. Same, those words mean the same thing. Relative risk would be the risk for one category, for example, African Americans. So you find the risk, 130 divided by 1512. And then you want that risk relative to another category, which is white, 87 divided by 2,900. You get what's called relative risk. Okay. Do that. Then you can say that African Americans are 2.87 times more likely to be let off than white Americans. Another way of saying it also, by the way, is you take your relative risk, subtract 1, and multiply it by 100. And that's the increased risk. So if it's 2.87 is your relative risk, then 187% is your increased risk. African Americans have a 187% higher risk of being laid off than white Americans. Okay. You can do all this, by the way, also with people not being laid off, right? You can find the risk of, I don't know if you want to call it risk, but you could say the proportion, the percentage of African Americans who were not laid off would be 1382 divided by 1512. Do the same thing for the white Americans, 2813 divided by 2900, and find the relative risk of those ratios too. Odds also can be calculated. And how do we find the odds of an African American being laid off? It's simply the number that are laid off divided by the number that are not laid off. That's the odds. Or you could say 130 to 1382. That's another way of saying that. You want to know the odds of an African American not being laid off, and it would be 1382 divided by 130, or 1382 to 130, just be the reverse. And then the odds ratio is simply the ratio of for both African Americans and for whites. You do the same thing. Shows you how to do it right here. For example, in this case, the odds of being laid off for African Americans is or are 3.03 times higher than for white Americans. And by the way, you can also make this into a percentage higher by subtracting 1 and multiplying by 100. So in this case, it's 203% higher is the odds for being laid off for African Americans than for white Americans. Okay, so that's the gist of chapter 12 in essence. All right, now let's get to my Excel spreadsheet. Let's make sure that's available. There we go. Now, one thing you can do to answer questions, if I give you a data set, either it could be 2 columns with an X and a Y, or it could just be 1 column, whatever. You can always calculate the mean and standard deviation of a variable. Now, if you have the data set in Canvas, in the test, you can simply copy those numbers over to Excel. I would recommend, I was having difficulties today with pasting the numbers, but if you use a paste special in Excel and just copy it as text, it will copy over perfectly. This, over here is an example of it right here. Actually, let's look at this Anchorage. I think we went over this in class here. This was the temperature in June and December for 8 cities in the United States. Right? And what if I wanted to find, for example, the average temperature or the mean temperature for June? Well, I would just go down maybe to the cell here, put an equal sign, and then the Excel function average. So you do equal and just start typing in average, and then inside the parentheses, you would just simply have the column here of values from N6, N13. So you just scroll down like that, and then enter it into that formula and hit enter, and you'll get your average. Standard deviation, it's stdev.s for sample, and then do the same thing, and you'll get your standard deviation. You do it for each of these columns. Mean and standard deviation takes just a second, so I would practice doing that. For those of you who know Excel or use Google Sheets, it's the same thing. Over here, I have correlation, C-O-R-R-E-L, so you do an equal sign, C-O-R-R-E-L, and make sure, then you have 2 columns, right? So 1 column, you do the same thing, you scroll down, and then you put a comma, and then do the other column. Close parentheses, hit enter, and you'll get your correlation. One of those slope of the regression line. Very important when you type in equal slope. The first set of numbers have to be your Y variable, whatever is Y. In this case, it would be December, but I would explicitly tell you which one is Y. So Y goes first, comma, and then the X. And that would be your slope. And the y-intercept, you use the function intercept, and do the same thing. The y's come first and then the x's. All right? So this is an easy way of calculating mean or average, standard deviation, correlation, slope, y-intercept. You can all do it in Excel just by copying over the data set from the test over to Excel. All right, that's it. So I'm done. I think it's almost time for your quiz. Any questions? Okay. So I hope I gave a pretty good review there for you, give you an idea of what's going to be on the test. So your quiz should be coming up shortly. It should be at 2:50. Please be sure to type in your answers accurately. That is, please don't make mistakes in terms of spelling and all, because it's very easy you won't get credit for it. So make sure that whatever words you're using, they're all in the book, that you spell it correctly. I try to, look for common alternative words that could be put in there, but I can't catch misspellings. That's almost impossible to do that. All right, so it's 2:50, and that's it. So no other questions. You can start your quiz, and again, stay online until towards the end of the period. I'll let you guys leave if most people have completed the quiz. All right, see you later. And I'm going to turn off the recording now too.